All right. So we move to the last talk of this conference. It's an immense pleasure to use Eder Correa from UNICAMP, who's going to tell us about Deformed Hermitian Yang-Mills equations on the direction of homogeneous varieties. Eder?
Okay, so thank you for the introduction. Firstly, I'd like to thank the organizer for inviting us. It's glad to be here, and thank you for the support and the opportunity. So in this talk, I'm going to give an overview about the Deformed Hermitian Yang-Mills equation in the general setting, and then I will focus on the particular case of reference varieties. Okay, so the plan for the talk is following. So I will start by giving some motivations and talking about some following conjectures in a quite general way, and then I will I'm going to give some overview about some resistance results following these two directions. One of them is about analytic approach, and the other one is a more algebraic approach. And then I will talk the particular case of version of this, right? The basic idea is trying to use some tools from representative theory, some symmetry actions of groups, and in order to simplify some problems which we had in the more general setting, right? So as we can see, the setting of version of this vector, the problem to solve the equation is not so difficult. We just need to know how to write some things, and then we can prove the basic resistance result. Okay, so let's start. So here I have start giving the definition of what is the Deformed Hermitian equation. So we fix a compact Kähler manifold, and we take one cohomology class. And so here I'm defining, as you shall see later on, so we need we need to be careful when we define this constant, which depends on the cohomology classes. So, but let's start. For a minute, we don't need to be worried about this. So the equation produced by Jacob and Yau is the Deformed Hermitian Yang-Mills equation. This is the equation. So the equation is analog of the equation which we had for special Lagrangians in the setting of mirror symmetry. So and for us, we also talk about in the particular case when the cohomology class is given by some holomorphic line bundle. So in this case, we say that the holomorphic line bundle, if you have a solution inside the first class, we say that the holomorphic line bundle admits a Deformed Hermitian Yang-Mills connection or a Deformed Hermitian Yang-Mills structure, right? And so here's just a brief motivation. So the equation was introduced by independently by Mariño-Minasian-Moore, Strominger, and Leung-Yau-Zaslow in these papers. And as I said, so the equation in the setting of mirror symmetries, the Deformed Hermitian Yang-Mills equation can be seen as the analog of the special Lagrangian equation. Okay, and behind this we have two Folklore conjectures, and the first one is about the characterization, or in some sense the equivalence between the resistance of special Lagrangians, some sort of class, and the notion of stability, right? And the mirror conjecture which we have for line bundles is about resistance of a Deformed Hermitian Yang-Mills connection. Okay, the line bundle resistance to be equivalent to certain type of stability. Here, the notion of stability is probably a very difficult problem. So both conjectures need to consider these two problems. The first one is related to the resistance of stability. Okay, So in order to study the conjecture, first we need to know what is the correct notion of stability to put in the conjecture, and then we attack the problem of finding the equivalence between the solubility of a geometric PDE, which is related to the existence of the special Lagrangians, and in the setting of homomorphic vector bundles, the Strominger-Yau-Zaslow space. So the equivalence between the notion of stability and the existence of solutions for certain geometric PDEs. This stability problem is a quite difficult problem, and we have some notions of the Bridgeland stability is the correct stability condition to approach. So it's in some sense it's a general notion of stability in triangular categories, which in some sense generalize and formalize previous notion produced by Douglas in more let's say more in the study of the physics behind the problem. Okay, and here we have a general principle. So in some sense, both conjectures are about the equivalence between stable objects and certain extremal objects. It's a quite general principle, but it's more or less what we have in these conjectures. Okay, so now I'm going to give an overview about some existence results. I'm not going to give the technical details because it's going on now, so I'm just want to introduce some what is known from the analytic approach of the problem. Okay, so we fix the Kähler manifolds in some homogeneous class, and then we define this. We pick some representative of the homology class and define this function. Okay. So here I'm going to introduce the notion of Lagrangian phase because we can the equation can be written in a more convenient way to work with geometric tools, right? So here the Lagrangian phase basically is defined as the arguments of the function and by that cochain, right? So once we have specified some argument, we have the Lagrangian phase associated to the pair, right? So we have a electron and the representative. So to each representative inside the homology class, we have a Lagrangian phase. We have a quantized description. So the quantized description is given basically in terms of the eigenvalues of the number is defined by decomposition. Okay. This description will be essentially what we are going to use in the setting of varieties, because if you suppose that everything here is homogeneous, okay, we have the Lagrangian phase is going to be constant. So the only thing you need to know to solve the equation is how to describe the eigenvalues using some tool for representation theory. Okay. So here, as I mentioned, so we have equivalence between the deformed Hermitian Yang-Mills equation in the form that I presented previously. So it can be written in this alternative way. Okay, and the question could be here written in the following way. So we say that a representative will be a solution if you satisfy this equation using the Lagrangian phase defined by the representative. Okay. The problem which appears here is to establish this equivalent description, we need to use a lift for the topological constant, which I have introduced in the first slide. Okay. And that's the problem because we don't know exactly if the lift exists, and other problem which we shall see is that depending on the lift which we have some tools available to use to solve the equation. So, in some sense, the first problem we need to solve is how to determine a suitable lift for the topological method. Okay. Okay.
Ask you why you
The Lagrangian space, the name, so as I said at the beginning, so we have a number between special Lagrangians and solutions of the deformed Yang-Mills if you want deformed Yang-Mills in something better. And the name is because if you consider, for example, if you consider the N with this standard Kähler structure, okay, if you pick a function, that's one function, and you look the special Lagrangian equation for the graph of the function. So the special Lagrangian equation for the graph of the function is going to be described in terms of the eigenvalues of the differential. And in some sense, we have a relation between the special Lagrangian equation and the deformed Hermitian equation. In many terms which we use in the setting of the deformed Hermitian Yang-Mills equation is motivated by this, right? So in fact, we have for example, we have the notion of mean curvature flow, which is like a thing in the second submanifold. And we also have an analog, which can be thought as a mean curvature flow in a sense. The name is just because they're not basically. Okay, so. Okay, so now I will just introduce the analytics in order to present some evidence results which we have from the analytic approach. So the first thing I'd like to introduce here is this complex number, which is given by the integral of some complex form which we construct from the initial data. And if the class admits a solution, we can show that the complex number defined this way needs to be different from the. So if we start again, so the first thing we need to ensure is that this complex number is different from zero if you are trying to find a solution, because if you have a solution, the number is different from zero. So the first necessary condition we have. So the second thing is a solution of the equation when it exists defines a unique lift. Okay? If the lift turns out to be exactly the Lagrangian phase of the solution. So if you have a lift for the topological constant, we have these two different types here. So we have the supercritical phase, which is the case when the phase is inside of this first interval, and the hypercritical case is when the lift is inside of this another interval. Okay, so these conditions, which I call supercritical and hypercritical, are important because from these conditions we have some tools from analysis to solve the PDA problem which we have in that equation. Right? And as I said, so if you have a solution, we know that you have a unique lift for the topological constant. And that's okay. But if you start, knowing how to specify the lifts without some existence of solution is a difficult problem, right? Because you can lift the angle, but we don't know where the angle belongs, right? The lift belongs. And sometimes, as I said, we need to use the lift to have some tools to apply the analytic problem. Okay. So here we have some results related to resistance from the analytic point of view. So in order to prove resistance from the analytic point of view, roughly speaking, we need to some conditions. For example, in the paper of Yau, they proved that we can have resistance if the manifold satisfies certain curvature conditions plus some hypercritical phase. You have a hypothesis, a geometric hypothesis on the manifold plus some condition on the phase. Okay? Once we have this, we can ensure the existence of the loop. The other results, we need to introduce the notion of subsolution, which is not a weak solution for the problem. The subsolution is a representative for the homology class for which the eigenvalues satisfy some extra condition, right? And so when we have a subsolution and some extra condition on the range of the Lagrangian phase of the subsolution, we can also prove resistance. Okay, and these assumptions are needed to ensure that we can apply some tools from geometric analysis. It's not just a matter of how can I say, for example, the range, the specific range, depending on the specific range, we have some tool, and depending, for example, in the first paper here, the supercritical range ensure that we can apply a certain tool for geometric analysis. In the second case, the hypercritical phase, which allows us to apply some geometric tools. Okay.
Excuse me, why we not consider?
I'm sorry.
We do not consider that the mission means why we need this I mean, without people twist by the
Okay.
one.
Without twisted.
There is any special element.
Okay. What happens without deformation? Are you asking about the symmetry on the side? Right? I don't know what happens without the deformation. Let me try this in another sample. Okay, the Lagrangian condition is equivalent the connection to be Hermitian around. So we have the semi-flat case, which is the specific example when we deal with the quotient bundles and find variety quotient by some lattice. In this particular case, we can understand better what is the exact relation between the Lagrangian, the complex side and the complexity, the complex side and the complex side. Okay? And as far as I remember, if you have just a Lagrangian, the Lagrangian is equivalent to the connection in the complex side should be the Hermitian. I don't remember it. So that's the result which we have in the particular case of rational homogeneous variety. So the result is basically probably someone could expect that the gene invariant representative inside the homology class turns out to be what we are looking for. And that's exactly what happens. And the nice thing here is that we can define, so the expression which appears here depending on some elements from representation theory, and it turns out to be exactly the Lagrangian phase of the gene invariant representative inside the homology class side. Okay. And as we shall see, so in this case, we have in fact the deformed, so the solution of the deformed Hermitian Yang-Mills equation coincides with the Hermitian Yang-Mills. In this particular case, the deformed Hermitian Yang-Mills connection is exactly the Hermitian Yang-Mills connection. Because the G variant representative is the curvature of some kind of connection. Okay, so I'm not going to discuss how to prove this right now. I'm going to try to do this at the end of the talk. So now let me just give an overview about some algebraic approach to the resistance problem. So as I did in the case of analytic, the analytic approach, we just introduce some basic ideas and notations to talk about resistance we thought. So giving analytics of variety, we can, with the basic data which I had introduced before, so we can define this central chart, okay? It's a complex number, taking the integral of the. So we have the exponentials, and we can in fact use this expression. It's the same thing. And so, in particular case, when we have holomorphic vector bundle, we can also define a central chart in a different way. So in the section when the E is the line bundle, we can go from one expression to another, space the same. And so that the notion of central chart is related to the notion of stability. So it appears in the literature of mathematics and physics. And so in the columns, Jacob Yau proved these results. So if we start with a solution, satisfying some supercritical phase, then we can show that this quotient of central chart, the imaginary part, satisfies this inequality for every irreducible. Okay, and they conjecture if the converse of this is true. Okay, if you have if this inequality is satisfied for every reducible subvariety, they conjecture that it might be possible to solve the problem. Okay, so we have some result which is more or less in the direction. So we have the existence of solution equivalent to certain types of inequalities involving the central chart. So for in dimension 2, we have this result from Jacob Yau and columns. So we have a result also for the low at a point in the case of projected space. And we have more general results here about some. So the assumption is supercritical phase plus some algebraic conditions. So by algebraic conditions, I mean some conditions involving certain types of integrals, like we have in geometric theory, things like that. Right? And the conjecture is precisely this one. So the conjecture is there is a solution for the Deformed-Hermitian equation in a certain class with supercritical phase, if and only if this inequality is satisfied. Okay. But we have, in fact, I put in red the supercritical condition because it's really necessary for the conjecture to be well stated in some sense, right? Because we can produce examples of non-supercritical solutions for which we have some inequalities in the opposite direction. I give an example in this paper. Right? If I have time, I will talk a little bit about this. Okay, so the conjecture was solved for some a great class of manifolds. So we have for the table surface, we have a slightly different version of the conjecture in the general setting. Okay, and this result is the more safe result for which the conjecture is proved for every projected, right? Okay, now I'm going to start to talk about the problem in the setting of Russian mononomial. And so I'm going to talk about a lot of things that probably we have seen today in our talk. Okay? Here, just introduce some notations and some basic generalities which you need to state the result. Okay, so I'm going to fix a simple connected complex simple group, and I take some characteristic of algebra and fix some simple system, and we have a triangular composition associated to this data. and we have a capital phi with set of roots. And so this part here is important. So to construct the manifold, we need to fix some parabolic subgroup. And here, up to automorphism is supposed to be standard form. Okay, so it's constructed, it's parameterized basically by subsets of the simple root system. So if you give me a subset, you prove parabolic subgroup. And the complex flag variety, or the rational means varieties, is given by this quotient. Yeah? And it can be seen as G manifold, where we have an action of some compact real form of G in the manifold. And as I said, so it's a complex different homogeneous. So just to put some notation for the presentation theory which we have behind. So with the basic data, complex simple algebra plus characteristic algebra, we can define the core roots. I introduce the core roots to have the fundamental weights, simple algebra. And here are the last weights. Okay. And okay, so this is important because as you shall see, this lattice is essentially isomorphic to some homology group of the flag varieties. So it's going to be important for us in the next slides. Okay, so let me describe briefly the homogeneous and bundles. So over flag varieties. So I'm going to follow this approach, which taking into account some elements from each theory. So we start with the principal bundle, which we have naturally setting. We can see the total space in terms of check cycles in this way. Okay, and for every character of the parabolic subgroup, we can construct associated like bundle. This is described in terms of check cycle this way. And from this decomposition, we have the parabolic subgroup. The character group of the parabolic subgroup is isomorphic the character group of a subtorial which we have inside the parabolic subgroup. And the generators for the character group is given this way. Okay. And here appears the complementary set of the I set which we choose to construct the parabolic subgroup. Okay, so here we have a correspondence between the simple roots inside the complement of I. We can associate to each one holomorphic in the bundle. And these guys, as you shall see, are the generators of the current group. Right? And here we have the Borel-Bailey theorem, which gives a correspondence between a geometric realization for the irreducible representations of the underlying complexity group. Okay. Here we have also some generalities. The important thing here is this isomorphism, right? The isomorphism between the lattice defined by P, the character group of the parabolic subgroup, and the character group of flat values. So here we have the arrows defining isomorphism. Okay. I'm going to denote by capital Omega alpha the invariant representative inside the term class of the generators of the character group. Okay, so here we have we can associate to every homology class, one homology class, an element inside the dual space of the characteristic algebra. It's not a integral weight, but it's a weight twisted by R because the coefficients could be real, and the coefficients are described in terms of this intersection number. Okay. And you can do the same for if you have a holomorphic vector bundle, you can associate to the holomorphic vector bundle element as we have in the case of an arbitrary homology class. And in this proposition, we can compute explicitly the eigenvalues of the endomorphism defined by this composition, right? And That is the number which appears in the formula of the main theorem which I presented before. Here we can compute explicitly everything. So if we start with the integral, which basically we use to define topological constants, we have this concrete expression. And the Lagrangian phase of the G-invariant is given by essentially the sum of this, the arctangent of these functions. And we can also compute the array of the first number. Here we have a remark because this effect implies that if K is a representative of some so if K is if the class is the first class of some line bundle, okay. So this equation basically says that the G-invariant representative has the constant traits with respect to the invariant field form. So it's if you pick a G-invariant representative, you can construct a Hermitian structure for which the curvature of the associated chart connection is exactly the G-invariant representative. It turns out to be a Yang-Mills connection. It follows from this fact. And so here we have the theorem. So once we know, so in general, we can compute the topological constant using this linear flowing theory because it doesn't depend on it doesn't depend on the representativity we choose to compute in. And we can pick the G-invariant and we obtain this complete description for the topological constant. But if you want to solve the equation, we need to suppose that everything is G-invariant, and from this we can, so the G-invariant representative is exactly the solution for this thing. And so this result has some consequences. For example, here also we have the name calibrated one form because we have some results related to the study of special Lagrangians, for which we have analog of almost calibrated Lagrangians. And so the definition of this space of almost calibrated one form is given by this capital H. And so it's the space of almost calibrated one form. So when this space is non-empty, it has a geometric structure with finite dimensional Riemann manifold with non-negative curvature. This is the goal of this paper by two columns and Lee. And we obtain as a people color these results. So fix it some G-invariant Kähler metric and pick any homology in one class. We always have this space. This space is not okay, so here in combat, I have talked about this previously. So, as I've seen, so the trace of the G-invariant is constant. In the particular case, when the class of size is characterized by the bundle, we conclude that the connection is a Hermitian Yang-Mills, and we obtain scholars or the deformed Hermitian Yang-Mills connection. This is exactly the Hermitian Yang-Mills connection. And here I'm going to just talk about some, it's not quite related to the existence problem, because as I said, in the case of plate varieties, it's quite simple to solve the problem. The difficulty is to find a way to write what you want, what you need. And this result is related more with the tools which appear when we are studying the solutions of the solvability of the Deformed Hermitian Yang-Mills equation. Okay. So here it's a result where we have using the same elements, we can describe, for example, the slope of holomorphic vector bundle just using the elements which I have introduced. Okay. So here we have a holomorphic vector bundle, and we have some Kähler class. So this slope with respect to the Kähler class has this explicit description. And in this formula, we see that just the element in the middle depends on the electron. So this guy which appears, the third element here is the volume, and the first is just a constant. And all the information which we need to study, for example, the varieties, the element in the middle. And from this we can obtain a result which gives, in certain way, so we can in fact describe solutions of the Hermitian-Yang-Mills equation using certain statistical charts. Okay. Let me just say what is P1 alpha. So P1 alpha, which are better, is equal to this one ratio. That's closure. So that's the third side of the plane. We can construct a curve of this type for every element in the set phi plus pi. So we compare this to the A of the second chart, and if this condition is satisfied, we can prove that the holomorphic vector bundle is admits a Hermitian structure solving the Hermitian-Yang-Mills equation. Okay.
This is just the Hitchin-Kobayashi correspondence.
Yeah, we need to use this. It's a combination of the Hitchin-Kobayashi correspondence and a result which we have. So, from using this formula, we can prove that if the restriction of the holomorphic vector bundle over all curves of this type are stable, then the holomorphic vector bundle is stable. It's more or less like that. So here I didn't put all the results, so it's just a part of this. By using this formula, we can, in some sense, obtain a criterion for stability, just looking what happens when we take the restriction of the holomorphic vector bundle to some specific rational curves inside of the triangle. Okay, that's all. Thank you.